Hello, welcome to Business Calculus, section 2.6. We're going to learn higher order derivatives today and why we might want to find the second or third derivative and what their meaning would be. In this case, it would be velocity is the first derivative and acceleration is the second derivative. Those are probably the most common, but there's other higher order derivatives as well. So a higher order, if you take the derivative of a derivative, we'll note it like this. Sometimes it's f2 sub x, denoting the second derivative, and then so on and so forth. F3 up there. So literally just taking the derivative of the derivative. There's all sorts of notation for it. This also means second derivative, this means second derivative, and this means second derivative. But we'll mostly be using this, and then when I get up here, instead of making 4 tick marks, I'll just put a 4 there, and then we'll put an n right there for the nth derivative. So, fairly simple. All we're going to do is take the derivative, in this case 8x cubed minus 6x, and then take the derivative of that. So the derivative of 8x cubed is 24x squared. The derivative of that is 48x. The derivative of that is 48. And the derivative of that, let's see, there's the first, second, third, fourth, and then the derivative of that would just be 0. By the way, if they ask for the sixth derivative, it would also be 0 because the derivative of 0 is 0, and so on and so forth. And here are some worked out solutions, which you're welcome. I would encourage you again to go to Blackboard, print off the worksheet that I posted there so you can kind of follow along. This says find the third derivative and then evaluate it at 2. So here comes the first derivative. Let's see, negative 4t cubed plus 6t squared plus 1. The second derivative, the derivative of the derivative. And the third derivative. I hope you all know by now I'm taking what? 2 times the negative 12 for a negative 24, decreasing the exponent by 1, and then if I decrease this by 1, it becomes a constant. So the goal now is then to evaluate the third derivative at 2. So I simply, every time I see a t, plug in a 2, and I get negative 36. Again, that has no meaning right now to you, but we'll try to get some word problems here in a moment. Notice that we just keep decreasing the exponent by 1, because when you take the derivative, it's 1 less. It gets a little bit more complicated, though, when you have negative exponents, when you have something like negative 1, because when you decrease that by 1, you get negative 2. So it's going kind of, so that's this next example. The derivative here would say what? Negative 1 times 1, which is negative 1, x to the negative first, which, negative second, which I think you'll agree that I could write it as negative 1 over x squared. So then the derivative of that, instead of taking, I can just say, oh, that's going to decrease by 1. But it's actually easier to take the derivative here. Negative 2 times negative 1 is a 2, and then when you decrease this 2 by 1, it becomes x to the third. Now you could have written it as 2x to the negative third, which would set you up for the next derivative, because I really want to kind of make sure I get a negative 6 this time, because I do the negative 3 times the 2, and that may not be as obvious over here in this form. So we usually leave our final answers with no negative exponents, but it sure is easier to think about it set up with negative exponents. So 6x to the negative 4, which you will write as 6 over x to the 4. And then the fourth derivative would be the 24 over x to the fifth, because all I'm going to do is multiply that 4 times the 6, just like I did the 2 times the 3. So you kind of see some patterns there, hopefully. So acceleration, by the end of this video, hopefully you know that's the second derivative. So whenever they talk about rates of change or the velocity, I want you to think first derivative, but if they talk over the rate of change of the velocity, or sometimes known as the acceleration, that's the second derivative. So again, the velocity is the derivative of the acceleration can be denoted as the derivative of the velocity. That would be the second derivative. The derivative of the velocity, which is the second derivative. So if height is the original function, the first derivative, we'll just call that s. Well, there it is. There's the equation of s. The velocity would be the first derivative. In this case, 2 times the negative 16, negative 32t plus 48. And then the second derivative would be the acceleration. Well, that's easy. That's just negative 32, the derivative of this, because that's a 0. But then they say, find the velocity at time is 3. So s prime 3 would be the negative 32. Let this t be 3. And say, well, the velocity is negative 48. The acceleration is constant over time. It's always negative 32. So again, worked out solutions here that I posted on Blackboard. This negative 32 is kind of an important concept. It's actually the gravity force on the Earth. So you'll see that negative 32 pop up time and time. Now if we go to the moon, it changes a little bit. But maybe you've taken another class where you've seen that negative 32 before. All right, so example number example 5 talks about the moon. Oh Lord, speaking of the moon. So, sorry I had to read this. Let's see. So this is the height, and they're saying find the acceleration, or how does that compare to the Earth's acceleration, which we kind of just mentioned was that negative 32. So let's go find the second derivative. The first derivative is negative 27/5 t plus 27. Second derivative would be negative 27/5. And we're going to compare that, negative 27/5, to the Earth's gravity. And to do that, we just set up a ratio. So we say the moon, negative 27/5, which is about negative 5.4, but you could take negative 27/5 and then divide that by negative 32. And we get, about 1/6. So it's about 1/6 of the acceleration. I wanted to show you example number 6 that we can actually use our calculator to look at multiple values, starting at 10 seconds and then looking at time be 0, 10 seconds, 20 seconds, 30 seconds, and we could just quickly calculate the different velocities which are given and accelerations. Well, to find the acceleration, we just take the derivative of the velocity. And to do that, what are we going to do? Low d high quotient rule. Low d high minus high d low all over low squared. And so we find out that the acceleration is about 400 over t plus 5 squared. All right, so now we've got a nice little formula for the acceleration, and we're going to use our calculator, and we're going to go to our y sub 1 and let that be the original function, 80x divided by x plus 5. And then the second function is 400. Now, I really like hitting alpha y equals and then enter and setting up a fraction, which some of you know that trick. I love this trick, except it doesn't work real well when I'm setting up table values. I'll show you here in a second, because I'm going to get a bunch of fractions, and I really don't want the fractions. But to set up your table, hit second window and start at 0, go by increments of 10, and then change your auto to an ask. So when you hit second graph, you can actually throw in there's the 20, there's the 30, here comes the 40, but notice that velocity function is a fraction, which I kind of want to change that back to a decimal. So don't use that alpha y equals fraction thing. Instead, let's just type it in like we had it before, 400 divided by, make sure you put this in parentheses, I'm changing the time to an x, of course, for graphing purposes. But then when I hit second graph, you can see everything's back in decimal form. And you can just ask it, because we've gone under second window and changed it from auto to ask, the independent. And then I could just ask for these individual values. Then once you have all those values, you can see, aha, the acceleration is approaching 0. And I think that was the goal of this problem. The last problem I just kind of wanted to review with you a little bit from a section from, I know this is section 2.6, but remember section 2.5, you might want to practice doing a problem like this again. It's difficult doing the product rule. So practice this, and then when you're ready, go ahead and pause the video right now and see if you can't get an answer. I have it worked out. I'm going to show you the answer here, so pause the video. I have it worked out right here. So you're welcome to pause the video on the solution after you try to work this out. The key here is maybe rewriting this as x times x squared plus 5 to the 1/2. And then doing that 1d2 plus 2d1. And then evaluate that derivative at 2. Every time you see an x, plug in a 2. So I'll leave you with that, a little review from 2.5. Again, it's worked out here. There's the equation of the line that they were asking for. I hope this video was helpful. If you have questions, email